Okay, and now we have the third paper of three different papers by Katie Hart, and this one is when linguists do set theory. Danger.
Okay, well, here I am back again. Okay, when linguists do set theory, a cautionary tale, and you'll see why it's a cautionary tale as we proceed through the material. When I started on Monday, I said that every lecture would have a lesson. I forgot to mention what the lesson was on Wednesday. Well, one lesson we could learn was that not every journalist knows what he's talking about, as you could see from the announcement in Nature about the paper that I was talking about. And the other lesson was that sometimes we exaggerate our results, trying to make them a little bit more palatable to the general public, I think. But I think in the case of Wednesday, the authors overplayed their hand a little bit. I think the independence was a bit of a red herring, the undecidability, but let's go to linguistics. So what happened? Well, almost 3 years ago, we had a short discussion on Twitter about the nature of books. And when you will download the slides from my website, you will find a link to that Twitter discussion, and you will probably be disappointed because the discussion is in Dutch. And so, well, maybe Google Translate can help you there. But the long and short of it is that the discussion was about the status of books. Well, a book is a sequence of symbols from some alphabet. And as such, it's a member of a Cartesian product of Cartesian power of such alphabets. And so you could argue, and that is what was argued in a paper that we were talking about, that all books already exist and have existed forever, because we were talking about those product sets all the time. But that is not what I wanted to talk about. This was just the instigation of all this. The paper was written by a linguist called Postal, and somewhere in that paper, and you'll find a link to that paper on my website as well, there was this sentence. Appealing to the reasoning of Langendoen and Postal, 1984, I'll come back to that in a moment, one can show further that the universe of books is truly vast, amounting to what set theorists would call a proper class. Okay, well, I could not let that one lie. I had to know what that was all about. What proper class? Okay. Yes, well, I started to look, and at first I couldn't find the book, which was a pity because I wanted to know what was going on. Later I found it, so I found it, but before I found the book, I found a paper, and I'll come back to that in a moment, that basically told the story that was also told in the book. When you read the book, you will be struck by, say, the tone, and I'll have something to say about that in a moment as well. And here is something that I have to say about the tone. Chapter 3 argues quite vociferously that there should be no size restrictions on sentences in natural languages. To put it into context, there have been theories, there are theories about how natural languages work, and you can look in the history and look at all kinds of famous linguistic names who have their ideas about what languages should be. And in many of those, shall we say, axiomatizations or rules or whatever, one of the things they write down is that, say, a language consists of finite sequences of symbols. And Langedun and Postel do not agree with using the term finite. They had all kinds of arguments for this in that chapter. Although they didn't quite convince me because they were sort of going overboard a bit. They bandied Occam's razor about a lot, using it not really as a guiding principle, as sort of an immutable law that you cannot violate. Here is a sample sentence from the book. Occam's razor forbids the incorporations of useless complications. Doesn't really, but anyway, this is how they used it. The mathematical meat of the whole thing is in chapter 4, and it's called the analogy with Cantor's results. Okay, what result of Cantor? I'll get back to that a little later. It contains their proof that a natural language, the collection of sentences, is what they call a mega collection. And the analogy in set theory is that we would say a proper class. It's not a set, it's a sub thing of the universe of sets, like the ordinals or the cardinals or something like that. And unfortunately, first I found this paper. It's called Sets and Sentences, and it's basically chapter 4. It has one advantage over the book. It's quite short. And the other advantage is that you can simply download it from Langedun's website. There is no trouble there. Later, I found that you can find the book at the Wayback Machine at archive.org. You cannot download it, but you can borrow it, so to speak. So what is in chapter 4? Well, it's the proof that languages form a proper class. And I'll use the word proper class from now on, rather than this mega collection thing. Now, I'll get back to this later, but for the moment, it's not really important what the rules are, because you can actually dismantle the argument, as I will do in a moment, without actually knowing what the rules are. But they show how to take smaller bits of language and combine them into larger bits of language. And okay, these rules will come back to haunt us later because there is something not quite clear about that as well. But you can simply think of what you do when you write. You take small bits of sentences or small sentences and combine them into larger ones using connectives, commas, semicolons, whatever. And after chapter 3, there are no rules that limit the cardinality of the sets of constituents that can be used. Let me repeat that. There are no rules that limit the cardinality of the set of constituents that can be used. There are no rules. And keep that in mind when we go through their proof in a moment. The central thing that our friends need to prove or want to prove is an existence theorem. And what is the existence theorem? Well, every set of constituents, so you take a set of sentences, then you can combine it into a bigger sentence. Now, it's fairly easy how you do that if the set is finite. It's not so easy when the set is infinite, but the authors claim that it can be done. And I also want to draw your attention to this indefinite article here. we are going to prove that if you give me a set, well, if we give them a set of sentences or constituents, as they call them, that you can combine them into a compound constituent. And like I said, you can read sentence for constituent, and compound constituent can mean bigger sentence, compound sentence, so to speak. And the argument for this is, as they say in the book and in the paper, straightforward. Yes, well, we'll go through the argument in steps. Take a set of constituents and call its cardinality K. The set is U is arbitrary. Its cardinality is defined. I should mention that the authors did pick up 1 or 2 books on set theory, and they know what cardinality means, I think. And we can just take ZFC and define cardinality by taking the shortest well order of our set, for example. Here is the first contentious sentence, at least in my eyes. Clearly, from a purely formal point of view, there is a coordinate compound belonging to the category Q. What I mentioned on the previous slide, there are categories of sentences, and so they claim that there is a compound that belongs to that category. Now, that sounds impressive, but it proves nothing. This sentence, clearly from the purely formal point of view, right, well, what? How does the formal point of view give me a sentence? There are no arguments, no indication where the W should come from or whatever. But I think I'll let this one slide because we're talking about languages, and okay, there is at least one sentence in your language, otherwise you don't have anything. However, again, this sentence is really indicative of the tone of the book. Whenever I'm reading bits and pieces in the book, I have people like Patrick Stewart or Ian McKellen reading those sentences in my head because it sounds almost Shakespearean, what they're the way they are putting their arguments across. Yeah, you should really need a Shakespearean actor to read the book to you, I think. Anyway, now, so like I said, we'll grant that there is at least one sentence, but now something bad happens, mathematically speaking. Since there are no size restrictions on the coordinate components, remember, we threw away the axioms that would limit the cardinality of sentences. There are no no size restrictions on coordinate compounds. W can have any number, finite or more than one or whatever, transfinite immediate constituents. So W is built up of whatever number of constituents we deem appropriate. Well, that's pretty bad mathematical style. It simply says there is a W that satisfies the requirements of a sentence. Fine, I'll grant you that. But suddenly, that one sentence has blossomed into a whole zoo of sentences, and we can immediately get them of all kinds of cardinality. And the real mathematical error here is that the authors threw away the size restricting axioms. To me, that means you don't have size restricting axioms, you simply don't have them. But what they apparently deduce from not assuming axioms is that you somehow have the negation of those axioms automatically, and that you can prove more if you throw away axioms. There is no moment in the book, not that I could find anyway, where they said, from here on, we will assume that there are sentences of arbitrary cardinality. They have only been arguing that we cannot forbid them, but there was never any construction of those things. Although there are a few, but I'll get to those in a moment. Anyway, it gets worse. W can have exactly K constituents. So remember, K was the cardinality of the set that we are trying to create a sentence for. And so from the arbitrary W, we suddenly have one that is quite specific, because we can make it have exactly many K constituents. Well, I beg to differ. Yeah, okay, so the set of subconjuncts, I'll get to the description of those sentences in a moment, but the subconjuncts are the bits and pieces that are connected through connectives into the big sentence, W. So we have a set V of things, a set like U, but V is extracted from this big sentence, W. They form a set of cardinality exactly K. Well, and the rules tell you that that is indeed the case. Every sentence that you have in your set is used only once when you build up bigger sentences. So you don't repeat and John, and John, and John. You will mention John just once, for example. That's part of, like I said, that's part of the definition, and we'll see the definition in a moment as well. Okay. Now, here, I'm giving you a warning, brace yourselves. We had an arbitrary set of constituents, right? We had some W that got progressively specific as we went along. And suddenly, W is going to be the big sentence that we built out of U. Okay, I don't buy that, because W and U were completely unrelated. And now suddenly, W is going to be related to U in that sentence. Okay, well, it gets worse. To show that W is a coordinate projection of U, all we have to do is, well, they say one-to-one mapping, but if you read between the lines, the one-to-one mapping is actually a bijection. We need to find a one-to-one mapping from U to V. And I wonder what that will accomplish. A bijection doesn't make sets equal, they'll just make them the same cardinality. And that's it. But that is trivial since two sets have the same number, since the two sets have the same number of elements. Yeah, right. That's how we define having the same cardinality. So this proof, this is the backbone of the construction of what is happening in the book, is completely bogus in my eyes. You start with two arbitrary things, and in the end, they're the same. And that's how you prove that you can construct sentences out of arbitrary sets of smaller sentences. Okay, so I don't buy this, and I hope you agree with me. But I'll just finish the proof, because if you remember, the chapter was called "The Analogy with Cantor's Results," and so you wonder, what is the analogy with Cantor's results? Well, they needed this existence theorem to actually get the analogy with Cantor's results. And what is that? Well, I'll get to this in a moment, we had a coordinate compound. We had a sentence that we could build from our set of smaller sentences. In this principle, they formulate a principle for their languages. And okay, the notation is also quite non-constant, I should say. Sometimes something is called S, sometimes it's SW, sometimes it's Q. They could have done better with that as well. But anyway, we're talking about the sentence that goes with the set. They have some pretty strange argument for that as well. Anyway, this is a reasonable principle for a language, especially if you only talk about finite sets. If you have a finite set of sentences, you can combine them into a bigger sentence, fine. But you would still say a sentence, but they have an argument why they can talk about the sentence. Anyway. And here is they're not content with just saying it in words. They make it really sound really mathematical by writing it down in a formula with a quantifier. So you have the collection of all members of the category S of a natural language. So category could, all kinds of sentences of all kinds of categories. They specialize in to subcategories of the language. You know, could say inquisitive sentences or declarative sentences or whatever. And CPU is that coordinate compound. So we now have a function. And they claim this is sort of an axiom. Every subset, its compound is also, again, a sentence. Fine. So this is a truth about all natural languages. Fine. And here is, they were hell-bent on getting to Cantor's results. And what result of Cantor were they hell-bent on getting to? Natural languages are not sets. They are mega collections. And the proof is just, suppose your L, your set, your collection of sentences is a set, then it has a cardinality. And there's another sort of misconception that you can see throughout the book and throughout the paper. Something is a set if and only if it has a cardinality. Well, you can sort of prove that in ZFC, but it's not the way I would prove that something is not a set. But anyway, say it has a cardinality, but it contains all the coordinate compounds of all the at least 2-element subsets of L, and the cardinality of that set of compounds is larger than that of L, and there's your contradiction. So they were working towards the equality that, the inequality that X is less than 2 to the X in the cardinality of X is less than the cardinality of the power set of X. And they wanted the analog of that in their language. But, you know, that's one way of showing that V is not a set, because V contains all. I'm not sure if V contains all the, yeah, it contains its power set, but you only look at the sets and so on. It gets a bit iffy, but that's an argument that's being used to show that V, a proper class, is not a set sometimes. Anyway, if the universe of sets were a set, then it would contain its power set, and then we would have a contradiction. Fine. Now, the proof is bad, as you have seen, that existence proof. But there is a there is something behind that proof that sort of collapses, makes the whole book collapse onto itself, at least chapter 4. The proof of the existence claim uses, without justification, as I just mentioned, that we can find compound sentences of arbitrary large cardinality. Those W's we could give them any cardinality we wanted. Well, that is an assumption. Like I said, we have thrown, well, we, Langendun and Postel, have thrown away the restricting axioms, but they haven't put anything into place in their place. But they make the sort of implicit assumption that because they threw away those rules, they suddenly get all kinds of sentences of all possible cardinalities without actually constructing them, I might add. So we can at best treat it as an assumption. But that assumption that there are sets of arbitrary cardinality in your collection means that that collection forms a proper class. It's equivalent. That there's an easy ZFC proof of that. So you can sort of summarize the proof of the main result as follows. If the sentences in a natural language form a proper class, then the sentences of a natural language form a proper class. I think we all agree with this tautology, but it doesn't prove anything. So in my eyes, the authors simply haven't proven anything. But there is more in the book. I see I'm halfway, and I'm also sort of halfway through my slides. Decent timing, I think. We had the definite and the indefinite article, if you recall. So now I have to explain how you do this coordinate compound constituent business. Here is a coordinate compound constituent thing. And okay, I'll give you all the ingredients here so that we can have a look at them. So we have a T. This would be, we called it W a few moments ago, but okay. It's built up of two things, the C1 and the C2, and the C1 is built up of two things, a connective and a subconjunct, a constituent, whatever you want to call that. Now, the empty set is sometimes used as a connective at the beginning of a sentence, because in English, for example, when you list something, the first item in the list doesn't have a connective in front of it. The second item in the list has a comma in front of it, and that can serve as a connective. And the final element in the list has the word "and" in front of it, and that can also serve as a connective. So the empty connective is a trick that linguists use to deal with this kind of thing. In fact, when the authors were doing their theoretic work, they were using one connective all the time. So they would have written this like so, because, like I said, they were using the same connective all the time. And there is a reason why I put Hardy in front of Laurel in this tree, and the reason is the following: this T is going to be called I used the word a few times. It's going to be called the projection. And Laurel and Hardy together, Hardy and Laurel, are the projection set. And this is what the definition on the next slide is trying to convey. So T is a coordinate projection, still indefinite article. U is the projection set. Yeah, that's Laurel, Hardy, Hardy, Laurel, the unordered set. That's the same thing. Each conjunct of T has an element of U as a subconjunct, fine. Each element is a subconjunct of some conjunct, fine. No element appears more than once as a subconjunct of any conjunct. So that's what we used in the beginning. Everything appears only once. So we were not going to make Hardy and Laurel, Hardy and Laurel, Hardy and Laurel as a sentence in our, that's not a proper coordinate projection of the set Hardy Laurel. We'll use Hardy and Laurel each exactly once. And this is, for me, another contentious bit. Suppose we have two members of our set U, Hardy and Laurel, and they occur as subconjuncts of conjuncts of Laurel. They occur in a fixed order. Note the word fixed. Okay, if they are of the distinct length, the shorter precedes, and that is why I had Hardy in front of Laurel. Hardy precedes Laurel. Now, if the things have the same length, use some arbitrary order. Okay, we have a fixed order that is arbitrary. I don't like that when students write that in their solutions to the problems. I want them to be a bit more precise. Anyway, this sort of looks a bit axiom of choicey like in the sense that okay, there is one thing that struck me throughout the book. The authors very proudly use all kinds of infinite stuff. But whenever you look at the examples, whenever you look at what they write down, I have the feeling that they were pretty much stuck in the finite situation. So if you have a finite set U, then you can order it linearly and it's automatically a well order, but well order is not important, I think. You always have a linear order at your disposal of the whole set. And I have the feeling that they were also a bit in the 19th century frame of mind. Yeah, we can order the set by deciding for every two elements which comes first and which comes second, as if by some mental process you could do that. Nevertheless, that's not very exact and certainly not the way we do it in set theory these days. But here comes the kicker. The last condition, the one with the arbitrary order, probably the word arbitrary, ensures that different orders of the conjuncts are irrelevant, whatever that means. And therefore, we now suddenly can talk about the coordinate projection of a set. I don't know what to make of this, because if you do a language, you create a sentence, at least you want it to be linearly ordered so that you know which comes first, which comes later. You don't want it partially ordered or unordered. And talking about arbitrary orders and then saying that, oh, now suddenly we have a unique projection, and that doesn't sit well with me. I would go as far to say that they don't define anything, so that the is misplaced. And still, I have no idea what the coordinate projection of Smith-Jones will look like. Assume some order. Is it and Smith and Jones, or is it and Jones and Smith? Because I can see a difference between those two. There was a TV series in the 70s called Alias Smith and Jones, and it wasn't called Alias Jones and Smith. And I think whenever people mention the two names, I think Smith sort of drops out first before Jones. So there is a difference. But they leave it undefined. And like I said, I don't really like that. And here is what I said before. They use one connective, one conjunction. And so then this is what I already wrote down a few moments ago. Okay. I tried to think of things that you could do. You could take a global choice function and pick one ordering for every sentence and do that. You can do something like Scott's trick. You'd simply say the whole set of orderings is the coordinate projection. You could leave the set partially unordered because they did say that shorter things come before longer things. And then you leave the things of same length unordered. And so the star here could be the and or the or whatever. I have no idea what they were thinking about, but they never ever really define. And I not define. They imply, but they don't. They are never. They seem to imply that they do something, but they never do it explicitly. And then there's the problem of length, because the book isn't over by chapter 4. It goes on to draw conclusions about natural languages. Given this vastness theorem, they want to, in one stroke of the pen, they discard basically all theories of natural languages that have ever been, at least before 1984, because all of them don't lead to proper classes, so therefore they cannot be the correct theory. But later in the book, they also, yeah, well, we talk about length of sequences, but okay, what are sequences actually? Well, this is actually in another chapter, I forgot which one, but they talk about sequences. And again, they don't really define them. They could have adopted the definition that we do in set theory, or in analysis, a sequence is a function with domain, the natural numbers. In set theory, a sequence is a function whose domain is an ordinal. At least that's what I teach in my set theory course. And basically every book reserves the word sequence for function with domain and ordinal. Anything else is just function. So they never define anything. Here's an example. Jack and his father are visiting relatives. Fine. Jack and his father's father are visiting relatives. Now, you can see where this is going. But I've taken this verbatim from the book. So they don't give sentence 4. They give sentence K. Jack and his father and his father's father and ... and ... And then there is a K here to indicate probably that we have K minus 2 fathers at the kth stage of this sentence. But they also give an infinite sentence. Jack and his father's father. They simply copy sentence number K and put an L of 0 at the end. Not an ordinal, but a cardinal. And that's throughout the book. All things have two things, and the second thing, I was getting ahead of myself. I have no idea. Well, okay, I do have an idea, but I'm not going to tell the authors this. What sentence sentence infinity looks like? We can infer what sentence 4 will look like. It simply has father's father's father, and that'll be sentence number 4. And we can recursively define sentence number k. Given sentence k minus 1, we insert at the proper place just before our visiting relatives k minus 2 fathers and 1 father, and that will give you sentence k from sentence k minus 1. But I wonder, and I strongly doubt, whether the authors can give an explicit description of sentence infinity. I can do something. I can use omega as my index set, and I have all these ever longer fathers. This is like the Monty Python Life of Brian scene, where they were talking about our fathers, and so on. And then here, I can envisage a sequence of omega many fathers, and then 1 father at the omega's place. But our friends never give an explicit description of that sentence. And the other thing is, what I started to say, they put an L of 0 there, and they only talk about cardinality. The length of something is always a cardinal. Length L of 0. Whatever that then means. And to show you what goes wrong when they try to do stuff with it, they describe a toy language, and I think I'll just have enough time to describe that language and what they do with this. They have a toy language which is not very natural, but never mind. And we only have letters as words, so we only have the words A and B. Each sentence begins with the word A, each sentence ends with the word B, so whenever you have a sentence, it looks like this. But, and this is a typical exercise from finite combinatorics, a counting exercise. In no sentence can the word A be immediately followed by the word A. So there is never 2 A's next to each other. And the word B can never be immediately preceded by 2 B's. So there is never 3 B's in a row. And discrete mathematics is an, count all the words of length K given this thing. That's a nice combinatorial exercise. But that's not what we're here for today. You can write down a few sentences. I copied these from the book. There was actually an error in their book, but that's not important right now. You can write down the first few sentences, and these are the sentences of word length 7 or smaller. And then they come up with a recursive definition, although they don't use the word recursion, they use inductive, by the way. Now, this set B, smaller than the set that I just written down, can be used as a basis for generating all the sentences in the language. How? Well, you can take 3 transformations. If you have a legal sentence, then you can turn it into a slightly longer legal sentence by doing this. You can insert a B between 2 final B's, and that's one thing you can do. You can add a B at the end if you want, and if you have AB at the end, you can make it ABB at the end. And if you do that, you can produce all the finite sequences that satisfy that those rules. This is how I would do it. The authors make things more complicated. I have no idea why. They have some collection of all natural language sentences. I have no idea where they find that, but never mind. The family F of mappings that preserves all defining conditions on sentencehood in L includes the mappings A, B1, and B2, the 3 that I just mentioned. Included in F are mappings other than those 3, but these can be ignored. So why take them on board? You might wonder. Well, I don't know. And so here is their definition. Remember the axiom of infinity in ZFC. There is an inductive set. Well, so they define inductive collection. And that's a collection that contains B and it's closed under F. Fine. Remember this. Well, I'll repeat it on the next slide. L is the intersection of all inductive collections over BF. Well, they rephrase it. L is the smallest collection of sentences drawn from US that is inductive over BF. Now, I know for sure that an inductive collection over BF has to be infinite, but they allow US to be finite, and then L is a finite subset of that set. So the mappings F are not fully defined, so to speak. Okay, you can sort of modify your F to cater to that. If US is taken to be a denumerably infinite set, each member, then L is the denumerably infinite set of sentences that is generated by the finite state grammar star. Okay, they had to throw in a few linguistic buzzwords here. Okay, this is another way of writing the way the words are generated from the initial set. Okay, now I can prove, and so can you, that in this particular case, the smallest collection, or what, as we saw on the previous slide, the intersection of all inductive collections is countably infinite and consists of finite sets only. Why can I prove that? Because the set of finite sentences that can be built from our B using the operations in F, that is an inductive collection, and the smallest inductive collection will have to be a subcollection of that. But it's also in every inductive subcollection, so it is the smallest subcollection. We can simply prove that L is countably infinite and consists of finite sets only. However, our friends are not bothered by that. If sentences are allowed to be of length L of 0, then it is easy to show that L has as many as L of 1 sentences. Okay, that's an oddity of the book. I didn't say this, but for simplicity, they assume GCH, the generalized continuum hypothesis. I think they weren't able to draw the Beth symbol. So they used Aleph, and therefore they need a GCH. And they wouldn't want towers of 2 to the 2 to the 2 to the L of 0 all the time. Anyway, there are as many, so for them, L of 1 and continuum are the same. There are sentences of length L of 0 that dissatisfy the defining conditions on sentencehood in L. Right. Okay, here goes. We show this by establishing a one-to-one correspondence, but all the things in quotes are quotes from the book, by the way. A one-to-one correspondence between a subset of L and the set of real numbers in the interval 0, 1. They don't use 1. I don't know why. But you can get 1 as well. And here's the argument, verbatim. So this string here, you can interpret that as 0. And this string, because you can alternate these two 5-letter strings at will, and you will always get a legal sentence. So if you take sequences of A's and B's that are composed of these bits and pieces of 5 letters, these two, then you can always get a legal sentence. And in that case, you can recode them by saying this is 0 and this is 1. Fine. Suppose that a decimal point is understood before the leftmost A in any sentence of L. Okay, that's a nice way of saying that A, B, A, B, B is 0.0, that's 0. A, B, B, A, B is 0.1, well, that will be a half. And then there are a few more. I think all 4 sequences of length 10 are given their binary. Oh, I think I made a typo here. I'll have to take this out of the slides before I put them on my website. Anyway, this is how they go about, and this is it. Okay, since by assumption sentences of L can be of length L of 0, there is a distinct sentence of L for each real number in the interval 0 to 1. Well, no. For one thing, the authors never ever exhibit a single infinitely long sentence in L. When you read the whole chapter where they do this, you don't find an infinitely long sentence. For a while, I thought I'd seen one, but I think I made it myself. The other thing is, how do we create decimal or binary expansions? Well, they're functions from the natural numbers to 0, 1 or 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And we interpret that using infinite series. We interpret those as real numbers. We need functions whose domain is the natural numbers. And that means that if we do this with the ABBAB and the ABABB, we get infinite sequences of A's and B's that don't end, that don't have a last B in them. And I'm pretty sure that the authors did not realize this. Anyway, that's another example, and I'll talk about our lesson in a moment. There is more in the book. There is a whole chapter 6 about infinite sequences, but I'm running out of time, I see. Sequence is left undefined. I already mentioned that. When you read the chapter on transfinite sequences, I get the impression, but it's only an impression, that sequence means linearly ordered set. So the domain can be a linearly ordered set like Q or the integers or whatever. They seem to have length L of 0, except the authors never explicitly say this. Length is not order type in their view, but it's cardinality, and I have really, I really dislike that. But it's almost 5 till, so I think I'll stop here. I filled my time, and I thank you for putting up with me. And if you want to read more, I put this stuff on my website, and you can enjoy the writings of Langdon and Postel there. Okay, thanks.
Thank you so much. This was quite a ride.
I tried my best.
Is there any questions here?
So I couldn't help but notice that, so they chose to only have the real numbers strictly less than 1.
Yeah.
But if they're allowing for arbitrary sequences of 0s and 1s, what about the sequence which is just all 1s?
I don't know.
I mean, that's 1, right?
Yeah.
Yeah, sure. I agree completely. But my feeling is, and I've said this once or twice during my talk, I think they're stuck in the finite.
Yeah, okay, I see.
And so their examples, and I copied that literally from the book. They only give 0.0, 0.00, 0.1, 0.01, 0.10, and 0.11. Those are the only real numbers they exhibit explicitly. So they probably imagine that when you do this, you only get numbers in the interval 0 closed, 1 open. That's the only explanation that I can find. I mean, this is akin to the discussion that, well, usually it used to be like that in SciMath, but now on Reddit and other fora, it pops up every now and then, is 0.9999999 and so on equal to 1 or not. Very many people don't want to accept that, so they pretend it's a number less than 1. So you don't get 1 from that infinite string of ones, in their opinion anyway. That's another explanation I could give for the absence of 1 in that particular situation.
It really doesn't help their case.
No, definitely not.
Okay, thank you.
And the only way in which they use infinitary connectives is by sequencing unary binary connectives and stuff.
Yeah.
That's also a problem.
Yeah, and whenever there is more in the book and in the paper, so you can enjoy yourself there. There's also a place where they basically do the iterated power set. They take the natural numbers, the power set of the natural numbers, the power set of the power set. So basically v omega plus 1 up to v omega plus omega. And when you start, when you start to think about orderings there, at one point, you're going to stumble on densely ordered sets. And I have no idea how the connectives work between points in densely ordered sets, for example. I probably, they didn't think this through enough, that's for sure.
But the funny part is that it can be repaired. You can make a setting in which it will work.
Well, everything should be well ordered, possibly, but yeah.
Okay.
But the really bad point is the thing I had in the beginning, where the proof. I would take a red pen and cross it out completely if I saw this on an exam.
The more, yeah, that one's good.
Any other questions or comments from the satirists in the room? What about the linguists in the room?
Yeah, it should be backfired with an analysis of what would actually make natural languages behave like this. When can you have that? What restrictions would you have?
Well, if you're interested, on my website, I will also put a link. This Langendun fella, he was in Arizona. I think he's retired now, but his website is still up. And on the website, you can find 8, I think, reviews of the book. Mostly by linguists, I think all by linguists, but there is one from Hungary who knows a little bit more mathematics than the others. And he already noticed a few errors, mathematical, in the book. But there was one review that said, well, I trust that the mathematics is sound, but...
Oh my God.
So they were really talking about the linguistic consequences of what was going on in the book. Actually, there was somebody who mentioned inaccessible cardinals as a possible way of dealing with these, but okay, let's not get overboard there.
Okay.
Hey, thank you so much. Let's thanks Katie Hart again.